We are live.
Okay.
Hello, everyone. Welcome to our Ask Me Anything with Dr. Milena. Dr. Milena Marjanović is a marine geophysicist and she's currently holding positions as a researcher at the Centre National de la Recherche Scientifique in Paris, France. And she's a research associate at Scripps Institution of Oceanography at the University of California, San Diego. She obtained a PhD from Columbia University, focusing on the distribution of melt at spreading centers. With a background in marine geology and geophysics, Dr. Milena has a wealth of experience in research and academia, including postdoctoral work at the Institut de Physique du Global de Paris. She is actively involved in promoting diversity and inclusion in the geosciences, and she has a strong commitment to mentoring and outreach activities. Dr. Milena is fluent in several languages, and she has a passion for sharing her knowledge and expertise with the global audience. Thank you very much, Dr. Milena, for joining us today. It's such an honor to have you in our Ask Me Anything session this month. Um, this Ask Me Anything session is going to be Dr. Milena is going to be sharing briefly with us her current research, and afterwards we're going to have an Ask Me Anything section with her where you guys can ask her any question about the presentation and also about her career. So if you have any question, please kindly post them in the comment section, and we'll bring them up along the line. So Dr. Milena, you have the mic. Thank you.
Thank you. Thank you very much for having me and for inviting me to the event. I will just share my screen right now with you. Okay, just a second, and just tell me if it's all okay. Is it okay? Can I
No, yeah,
now?
it's okay.
It's perfect.
Perfect.
Okay.
It's okay.
So before I start talking about what I do, I will give you just a brief overview of one thing that I work on. I wanted to actually lead you through my career path. So I was born in Serbia, where I did my bachelor's studies at Belgrade University with a major in applied geophysics. After graduating, I moved to the US, to Columbia University, to pursue a PhD program at Columbia University in the US, where I graduated in 2013. But along the way, I also did a couple of internships with industry. And this is one of the points that I would like to emphasize, that it's really good if you can, regardless of your current or project that you're working on, it's always good to take the opportunities to get to know other options and other branches of your field. So I was very happy working with Exxon and ConocoPhillips, and in somehow I continued this kind of close relationship with industry, and even after I graduated. After I graduated, I decided to go from the US to Europe, to France. And I would like to also emphasize that at that time I didn't have any job option in France. I just did the gap year, where I was trying to apply for a fellowship, Marie Curie fellowship. And if you are interested, we can talk about that in the second part of this event. So ask questions. And one part of this fellowship was designed to spend at the Institut de Physique du Globe de Paris, which is Institute of Physics of the Earth in Paris. That I also spent in the Netherlands working with Shell. And what some of the results that I will be showing you today are results of this close collaboration with Shell. And since 2021, I hold a permanent research position that is given by National Center of Research in France. So it's a sort of a government job. And I'm based at the Institut de Physique du Globe de Paris. It's a pure research position, so I don't have to teach. I can only focus on working on research problems. Since summer 2023, I also hold a research associate position at Scripps in the US. As a marine scientist and as a marine geophysicist, I do quite a lot of seagoing expeditions. This is the map that shows the distribution of past cruises that I did. They're shown, most of them are shown in black. Those are the past ones. The most recent one is in white. That's the one that I just completed about a month ago. And one particular interesting thing about this cruise was that on board we also had the famous submarine Alvin, and I got the chance to dive and go to the seafloor at about 2,500 meters, which was truly amazing. And then in this brown one, I'm showing the project that I have funded, but I still don't have the date for the cruise. And there are several cruises that are in planning, the projects that are going to happen. So there will be quite a lot of more ships on this map. I do, as a seismic person, I do acquisition of controlled source seismic data. I do the processing, interpretation as well. In collaboration with industry, I developed some geophysical techniques to analyze the data. And mostly when I do the interpretation, I'm interested in understanding the processes by linking magmatic and hydrothermal processes, and also tectonics. So now I would like to give you just a brief overview of one of the things that I'm currently looking at. So I will take you to the specific rise, 9 North. It's one part of the vast mid-ocean ridge system that is shown in this beautiful artistic representation of our planet, where mid-ocean ridges are presented here, and they are often defined as the longest mountain chain that wraps around the globe in the length of about 60,000 kilometers. One part, as I said, is the Pacific rise. This is where two plates are separating, the Caucasus and the Pacific plate, at a rate of about 110 millimeters per year, which makes it one of the fastest spreading center on our planet. As the plates are separating, they give rise to new oceanic crust, and the place right beneath the ridge axis where the plates are separating is characterized by a magma reservoir that is built of mush and this prominent feature that's a magma body, which we call axial magma lens, which we'll be looking in the slides that will come. Why these specific rise is interesting to study. This is one of the most dynamic part of the mid-ocean ridge system. It had an eruption in 1991-92. It is also very well known for its hydrothermal system, hydrothermal activity. This is the distribution of hydrothermal vents. High temperature ones are represented in red stars, where low temperature ones are represented in blue. But before I go ahead, I would like to step back and explain what hydrothermal venting is. So this map is showing the distribution of hydrothermal vents that we know that exist. And the specific rise is somewhere around here. What we think is happening there, we have the cold seawater that is actually penetrating fractures and fissures, going down, interacting with minerals, with rocks in the crust. And as it goes down, it gets heated up by the latent heat of this magma body. We all know that the hotter water is more buoyant, so it tends to go up. And it goes up typically at the places where two plates are separating to form these beautiful black smokers. At the black smokers, they are not just impressive features, they are also important because they are inhabited by different living creatures. Some of them are shown here, from crabs, tube worms, etc. And the conditions that are currently operating, that how they live, it's believed that they could mimic the Earth at the moment of formation of life, onset of life on Earth. So that's why they are important for us to study them as well. They became very important for also mineral resources, for deep sea mining, but I'm not going to get into that topic today. So let's get back to the specific rise and our distribution of vents. I would like to highlight two vent sites, Q and M. And in the time when a scientist went to actually explore these vents in mid-90s, so 1995, they saw very active hydrothermal activity at these two vents. However, they repeated the same thing in 2006, 2007, and they saw that these two vents were completely dead. There was no activity at all. There were no living communities around. So the question is, what happened between these two periods? In fact, in between these two years or periods where we had an eruption that happened in 2005, 2006. And not only that we documented this eruption, we also recorded this eruption. As the area is highly dynamic, researchers wanted to monitor it. So basically they deployed many of the OBSs in this ocean bottom seismometers to monitor the activity of this place. So they would typically, from 2003 to 2007, they would go deploy the instrument, leave it for a year, then come back, recover, take the data out, and change the batteries, and then deploy the instrument again. So they went for this routine kind of activity in 2006. And they realized that they could communicate with the instruments, but they could not lift them up. And so they sent a robot with the camera, an ROV, Jason from the US, that actually realized that there were new lava flows that trapped the OBSs. And luckily, in this whole thing, the robot was able to release the instruments, and some of the instruments kept the record of the eruption, and you will see the record in several slides. This was also the place where, for the first time, we imaged the magma body. At that time, it was called axial magma chamber. This is the reflection signal from late 70s, and this is from late 80s, 2D seismic sections where you can see the reflection of this magma body on the top of the magma reservoir. This was very important finding because it moved to introduce a new concept of crystal mush paradigm, which was actually suggesting that we don't have like a huge reservoir filled with melt, but instead we have a reservoir that is filled with mush with the topmost magma body. This concept was transferred to subaerial volcanoes. So this kind of images of old encyclopedia that showed great big magma chambers were replaced by this crystal mush paradigm. As the technology was developing, we had better receivers, longer cables, more powerful sources. So we were able actually to penetrate deeper. And so instead of imaging only the shallow magma body, we were able to penetrate into the lower crust and image additional magma bodies that are shown here. And this finding was very important because it provided the evidence for the way the oceanic crust is formed. And you have to keep in mind that oceanic crust is representing about 70% of the Earth's solid surface. There are two end member models for explaining how oceanic crust is formed. One is suggesting that we have one single magma body through which all the melt is passed and to form the oceanic crust, as it's illustrated here. So we have diking, eruption, or basalts, and then there is also crystallization, and those crystals are sliding as the glaciers, and that's why it's called Gabbro Glacier model. In the model that is actually supported by seismic data, instead of having a single magma body, we have multiple vertically stacked magma bodies that are contributing to the formation of the crust. In fact, this kind of view was also very appealing for subaerial volcanoes, that represent huge hazard for people. And so now, instead of having just one magma body and mush, we have basically a magma reservoir that is represented by vertically stacked magma bodies. And that's coming from the studies that we conducted at mid-ocean ridges using seismic data. All these novelties or these results that I've been showing are coming from 2D data sets, but now the question is, how do these magma bodies look in 3D? What is the role of these of the magma body architecture in volcano construction and evolution, and where and how dikes nucleate? To look into the 3D of third dimension of these magma bodies, in 2008, we went and collected seismic data, 3D reflection seismic data. This panel here shows the ship tracks that we did in 2008 when I was a graduate student at Columbia. We used capacity of Marcus Langseth, the only ship in academia that we have that can tow simultaneously 4 streamers that are 6 kilometers long. And we covered the subsurface of about 30 to 40 kilometers square. This panel here shows the 3D view of the seafloor and also the seismic section brood stack where magma body is not perfectly imaged. To actually improve the imaging of the magma body, I had to obtain a better velocity model. And to obtain better velocity model, I teamed up with experts from Shell. So I was using their advanced elastic 3D elastic full waveform inversion code. And thanks to these velocities that I obtained, I was able to migrate this volume and obtain the images that are much better. So now this is how I see the magma body. In some places, this magma body is relatively simple. In some places, it's quite complex. But you have to keep in mind what I was showing you before. The data were collected in 2008, and this paper got published in 2023. It's a lot of effort to actually process this data and come to these beautiful images. But as much as I like to look at these images that look like an Oreo cookie, I think the best way to appreciate the changes in geometry of the magma body are through 3D, through picked horizon. So this is the magma body as a seismic horizon that was made by picking these reflection events. The colors are representing the depth variation of this magma body, with the red color representing the shallow parts and the dark blue to black representing deeper parts. This is just a view from east and west. And one of the message that I want to convey with this slide is that magma bodies are not flat. They have important topography. And this is really important when we think about where the dikes are forming for melt to, or for magma to actually propagate towards the surface. As we don't have much time today to go and look at all the details of the magma body, I will focus on one particular part. which is the central part of this magma body. So in this panel here, I'm showing the plan view of the bathymetry with the outline of the lava flow that tracked those instruments, ocean bottom seismometers, in 2006. This is the plan view of the magma body, and this is the same outline of the same lava flow, just for comparison. We are going to focus on this area here, so that's zoomed in part in here, because we think that that's the part of the magma body that contributed the most to the eruption event. In particular, I want to focus on this feature here, which I call depression or trough. I outline it here so you can see it a bit better. It has its northern part that is a bit deeper. It's about 72 meters deep. I call it head, but that's not geological term. And in this kind of head of the depression, we have most of the microseismic events that were recorded that we were able to recover from these trapped OBS instruments. They are represented by these dots, gray and black. The difference between black and gray is nothing but the fact that the black ones are the 50 strongest events. They all happened on one day, January 22nd, 2006, and they are believed to be the main diking event for the eruption. And in fact, when you look in the cross section, you see that most of these events are falling at the depth of the magma body, which suggests that the diking was actually sourced from the magma body due to overpressurization of this reservoir. Another very important observation is that this head of the depression is perfectly aligned with the plate boundary, or we call it geologically axial summit trough. That's the innermost zone, accretion zone. That's basically, if you would have to draw a line between the plates, it will be through this zone. So it will go like this. In this head, or the northernmost part, we have perfect alignment, whereas in the south we have some of the some shift. And so what we think it's happening here in this northern part, where we have the dominant diking events, we think that because we have this perfect alignment, melt was basically able to go vertically up without any problem. But in this part, southern part, we had some mismatch. So one part was going up, but the other part, because the pressure was not sufficient, actually resulted in accumulation of another shallower magma body, which is actually shown as this red patch here. One very interesting thing is that when we compare the volume of the trough, so the total volume of this trough, with the volume of this shallow magma body, the dike, if we assume the thickness of the dike, width of the dike, that is 1 meter, and the volume of the lava flow, we get perfect match, which is actually the first time that we could do this kind of surface-subsurface comparison for active volcanic system. Now, I will finish this short talk by the fact that now we have the 3D image, but what we would like to see is how this magmatic system changed in time. So we have a proposal to actually go back to the same place and do a repeated seismic survey known as a time lapse to actually see how this magma body evolves in time. And with this, I would like to thank you, and I will finish the talk and take questions.
Thank you very much, Dr. Milena, for that great presentation. Um, if you have any question, please leave them in the comment section. So without wasting much time, I would like to move on to the Ask Me Anything session. So I guess when they post their question, I'll bring them up.
Mm-hmm.
All right. So without wasting much time, could you elaborate on why you chose to become a geoscientist? Was it only to prove a teacher wrong, or were there factors that actually influenced your decision? Thank
Okay,
you.
so that's a question that. So it was not to prove the teachers wrong. In high school, when I was a high school student in my home country, we have this kind of what we call research centers that allows high school students to go and experience have experience real research experience in the fields that are not part of common curriculum in high school. And for me, that was geology, and that's how I learned about plate tectonics. And as I liked physics, I thought, okay, it will be great if I could use physics to study plate tectonics, and that's how I became a geophysicist who studied mid-ocean ridges.
Thank you for that. I think it's quite interesting. I was also very interested in geography, and I really loved it. So it's just a natural thing for me.
Yeah. Mm-hmm.
So first, before I ask this next question, can you just explain what inversion is exactly?
What is
What what is inversion?
in
What
fashion?
yes,
In terms of geophysics.
yes, in terms of geophysics.
So I don't think to be honest, I don't believe in this fashion thing because it's like that comes and goes. Depends on the time when you ask. So when I finished my studies, for example, when my graduate school, mid-ocean ridges were really not in fashion. You could barely find a session to submit your abstract if you were working on mid-ocean ridges, but I persisted because I loved it. And so I really don't think that we should pay attention of what's in fashion. Mid-ocean ridges are by the way back in fashion. Many people are working on them right now, but I don't believe in what is in fashion. I'm more motivated by my own uh, thinking, by my own motivation, but what I like. So I don't really pay too much attention what is in fashion.
Thank you for that, ma'am. So, can you share an insight into the 2D and 3D full waveform inversion techniques in studying the hydrothermal processes in the oceanic crust?
Okay. So yeah, I did for to use to produce the results or to look into the processes that I explained just in the presentation. I used both 2D and 3D full waveform inversion. And the 2D I used at the Institute, it's relatively easy because it doesn't take too much computational power to do it, whereas 3D it's very heavy, it's computationally very demanding. So I was not able to do this at the Institute. I had to team up with industry to do it, and that's one of the reasons why we had to wait almost 15 years to produce these results that I showed, because we couldn't do this kind of processing, this kind of like modeling, velocity modeling for in at the Institute. I don't think that actually many universities have the computational power that is necessary. So one of the big differences is the computational power. 3D is very demanding. There are much more parameters that you have to tackle. And then when you also prepare the inversion, you have to be very careful because for the 2D, you can test different options multiple times. But for 3D, you really have to focus on very small subset of your data, test everything, and then when you are happy, you just send it, and it's one time go. So you basically do it once, and in fact, for when I was at Shell, we did it for 3 months. So basically, to obtain velocity model, I was running the inversion for 3 months. So it's really a big difference in time scale, and it's much more difficult to actually prepare the data and parameters.
Thank you for sharing that, Dr. Milena. With a lot of experience in collaborative research and that has attracted funding, what can you say are the key components to successful research grant application?
Um, I think that you have to have a good idea. Normally nowadays you have to have something that they call a fundamental question, or the question that is so you present a case study that is going to actually respond to something that many people are wondering about. So, for example, how oceanic plate is formed, or how the melt propagates, or that kind of like a global question, or is there water on the moon or Mars or something like that. That's some kind of global. You have to start from a very the fundamental question, and you have to present it really really well to be successful. There is also this kind of like, yeah, of course there are different calls and um, that are related. Yeah, I agree that sometimes you have this kind of in fashion topics like climate, I don't know, yeah, things like earthquake hazard. This is always in fashion, so there are calls that are in particular sensitive to this societal impact, but then you have to choose where you submit your grant. But I think that the key is really a fundamental question that you want to ask, and yeah.
Thank you. So you must ensure that your research is actually solving something, and it's gonna give an answer to a question that people have been wanting to know.
Yeah.
So thank you for that, Dr. Milena. What are some of the emerging trends or areas in research that in the marine research geophysics that you're studying, and that you find that are particularly interesting or promising for future exploration?
So yeah, once when I was actually reading, and it was actually published by SCG. There was a really nice article when I finished my graduate studies, undergraduate studies actually, and it was an article that was saying that you don't go for trends, because something that is actually trending now doesn't mean that it's going to trend in 5 years. And now it's very attractive to work in artificial intelligence, machine learning. So application of machine learning in seismic, it's very popular, but we don't know for how long that will be popular. So I still think that if I would be able to give an advice, it's really to motivate yourself by your what drives you, what you want to do, not by the trends. But if you ask me what is popular right now, I think it's the application of machine learning.
Thank you for that answer, Dr. Milena. Um, you're in a male dominated field. And so, what do you think are the mistakes that you have seen women make at work that prevents them from taking charge of their career, or ways in which women hold themselves back from reaching their full potential?
Oh, that's a difficult question. I don't think that we are making mistakes. I think that it's really the way the society is organized, and how society shapes us, that we react to that kind of society. And I see in myself that I hesitate more than my male colleagues. So I think that that's, if I can call that a mistake, I would not call it mistake, but maybe a behavior that is not giving us as leading to successes as we could, to reach our full potential. I think that we hesitate a lot. You can see that when you publish a paper, and compare a paper that was prepared by male and female colleague. Female colleague will address every single detail, every figure will be perfect. She will give 100% to that, whereas male colleague will leave some things like yeah, doesn't have to be perfect. Whereas for female, it has to be perfect. You can see also that when female researchers give talks. I have just been to a conference 10 days ago, and I could see that all female researchers were right on time. They respected the time. They respected the time for questions, whereas male colleagues were, okay, I cannot finish my talk. The time is up. So I can see that women are putting much more effort to prepare, to look perfect, because we think that we are judged harsher, and because we are hesitating a lot, we tend, actually, people tend to judge us harsher. So in that way, it's I think that we should just go for it. Even there is a statistic that was done, and it's very well known, that when you apply for a job, women tend to apply for a job only when they fill up all the criteria, whereas men would apply even if they fill up 50% of the required skills. So that's something that we may need to learn, but I think also the system has to change. It's not only one-way street. It's really two senses, two directions that need to work together to improve.
Thank you for that answer, Dr. Milena. So this leads me to the next question. Do you recall any instances in which you felt disrespected, and how did you respond to that circumstance?
Yeah, I think that there are quite a lot, actually. Unfortunately, there are quite a lot, and they as you climb the ladder, they become more frequent. From very small comments. I got, for example, a comment that when I got Marie Curie fellowship, that I got it just because I'm a woman. And in fact, it was not the case, because 67% of awarded researchers were men. So in that way, it was disrespectful for the funding program. It was disrespectful to me. It was really diminishing my work, from the fact that people are just giving you, like, they're simply disrespecting your work. And in that kind of instances, the good thing is that they are becoming more frequent, but the fact that you have permanent position gives you more power to actually choose with whom you want to work. So my way of defending is giving them the real statistics. For example, in that case of the answer of Marie Curie fellowship, but in the instances when it's really from a colleague that is really trying to go against my work, then I simply reject to work with that kind of person, and that's my choice, and I'm free to now choose with whom I want to work. So that's the way to respond to this kind of behavior.
Thank you very much for sharing that experience with us, Dr. Milena. Um, how did your involvement in organizing workshops and events such as the SLEEDI and the EAG conferences contribute to your professional growth and networking within the geoscience community?
Um, Doing things for the community, it's very rewarding. I think that that's something that helps you meet new people and develop new projects. It's also on personal level, they're very, very nice. I'm very happy to participate in the activities that are organized by EAGE. And my involvement was really with the Women in Geoscience network, and I worked a lot. I was one of the committee members who established a mentoring program. So it was very hard to establish a program at that time. and to run it. I was also a mentor through that program, and I had a mentee. Initially, that mentee was meant to be for a year, but then we extended that to 4 years, and now we became friends. So it's not only networking; it's also you expand your personal friendship. But you also learn quite a lot, and you also can establish a network that can help you in your career. For instance, this last project that I was mentioning, the time lapse, the first instance, because it's also going to be something that is going to be established as a collaboration with industry. The first contact that I had was really through the network that I established through EAGE, for example. So it's helping me. I helped, but I'm also getting the reward of being helped through in a different way. But the network is very important part of my work.
Thank you very much, Dr. Milena. Particularly the EAG mentorship program that you created, you contributed to creating. I am a mentee this year, and my mentor is Dr. Remel. Yeah,
Uh-huh,
so
uh-huh.
yeah, it's really great to be able to connect with people from the
Yeah,
industry. Yeah, and I hope that we can also extend it. And I know we're going to extend it, and it's going to be an integral part of my life.
yeah,
Thank you.
no,
So
it's
thank you.
yeah, it's a really nice initiative, and I think we had a lot of fun when we were establishing it, because we had to design all the rules and the way how we connect people. It was really fun to connect students and mentors and mentees. And yeah, I think it's a very valuable thing. And from the comments that I'm getting from mentees and mentors, the feedback, it's always positive, and I really like it.
Yes, yes, thank you. So what are some of your success habits? What what do you do? Can you tell us your
Whew.
secret?
I don't know. I mean, success, it can be defined in different ways, but if we talk about, like, let's say success in writing a grant application, I would say that for me, what it works is to think about the deadline that is not the real deadline, but I put like the deadline, I put like a clock a bit forward. So if I have to submit something, let's say on June 30th, I would say my deadline is June 20th. So I behave, I organized my time as the deadline is 10 days before, and I have everything ready much more in advance, so I can give the project to a colleague who can read and who can give me a feedback, so I can do the last minute changes. I also don't worry about the problems with the submission jam due to internet or connection. So that's something that I really like, and I try to do every time when I need to submit a project. Even for the abstracts for the conferences, I like to do it in advance. So I developed this kind of habit of doing things in advance, so I don't have to deal with the last minute stress. I don't think that I can work under pressure, but I think that performances under pressure and when you have time are very different. So I choose not to work under stress.
I think that's very good, and I think it's going to be nice if students like us can also cultivate that, because we are used to doing things in last minute. And another thing is that when you have time, you can always make your application better. When you have time, when you go back to look at it, you always see something that you can
Yeah.
actually add to it to make it better. So I think it's a really good um,
Mm.
thing to add to your habits. So yeah, thank you for sharing that, Dr. Milena. What are some of the key challenges that you have faced in your research, and how have you overcome them to achieve those your goals?
Um, There are a lot of challenges that you have to. For example, for me, when I was applying for a job, a big challenge was to convince the community or the committee that what I'm doing is important. And it's because if you think about marine sciences, we spend quite a lot of time at sea, and everybody sees that as a high cost that is not necessarily worth the value. So one of the big challenges for me was really to show with my results that the data that we collect are really valuable. It's not one project, it's not one paper data, it's data for decades that you can exploit. And the example that I showed, that we collected the data in 2008, and I come to actually show the 3D images of the magma body in 2023. So it's 15 years after. That's something that was a big challenge to come to the point to show, with the right technique and the right partners, I can actually do a good job. So it's there are quite a lot of challenges, and normally it's actually convincing people that what you do, it's significant and it's important. I think that's I think the biggest challenge for me. There are also some challenges, like physical challenges when you go at sea, and you have to do, I don't know if you've done, some of you may have done it, but when you want to join a research vessel, you have to go to do this survival training at sea, and that's something that is very not pleasant. I'm not like somebody who likes a lot of adrenaline, and it's quite tough. So that was one of the challenge that every time when I go at sea, I have to overcome. Yeah, like jumping from the big height and all that stuff. So yeah, so there are a lot of things, from mental challenges, proving somebody something, and challenges in terms of physical strength.
Thank you for sharing that, Dr. Milena. I also don't like a lot of adrenaline, so I've not been at sea before. I've not been at sea, so but I think, yeah, it would be nice to be at sea and you know, push the limits, right?
Yeah,
I can do
yeah,
it.
yeah. No, sometimes
If you can do it,
it's
then I can
pushing
too.
too much.
Thank you for sharing that, Dr. Milena. Okay, so what advice do you have for students interested in pursuing a career in marine geophysics, especially in terms of developing expertise in geophysical techniques and data analysis?
I think that one advice that I like to give everyone is to, when they are working, regardless of working in industry or in science, in academia, is to be curious and to be driven by their own, what they like to do. Um, it's everything else comes along. I think it's if we worry too much to actually adapt to the current situation, we lose our interest, we lose our motivation, and then we are actually risking to do our job as a routine and not be happy. So I think that especially if you do research, you have to feel the happiness to like it. So I think that the motivation, do what you like. It's very important. And also, if you think about whether industry or academia, I'm also not the person who is going to strictly separate those worlds. If you can combine them, I think that works the best. And if you are wondering whether to go first to industry or academia, I don't think that the order matters. You will see. I mean, you can try one thing, and if it doesn't work, you go to the other, and you can also combine them. So I think that having experience is never bad. It's always going to be a plus.
Thank you for sharing that, Dr. Mineta. I also think it is important that you follow your passion, because then
Mhm.
it's not gonna look as if you're working. It's gonna look as if you're doing something that you enjoy, and you're getting paid for it. So yeah, I'm a big fan of that too. So, Dr. Milena, how do you balance your research commitments and public engagement? Creating mentorship, doing a lot of stuff and organizing events. What strategies do you use to manage your time effectively and to, balance it with your, personal life, your family, just,
It's
how
I
do you
don't know if
do it?
it's very balanced. I would say sometimes it comes to the point that it's not very balanced. But I think that it's really the fact that I do what I like, and that drives me. That's actually motivating me to when I see. I do quite a lot of outreach, especially for promoting women in science, because I think that that's something that we are missing. And if I see one woman that decided to follow the path for me, that's very satisfying, and that's something that is actually motivating me to find the time um, to do this kind of stuff. And I think that it's also what I see as the outreach and this kind of activity. I see that's part of my daily work, so I try to actually put it as part of my daily job. I don't think that the fact of I'm doing something, writing a paper, is going to be important if I don't share my experience and my results with people. And I also have to learn how to communicate. So if I do it in a way that nobody understands, then that doesn't serve anybody. So I think that effort is really rewarding, and that's why I do it.
Thank you for sharing that, Dr. Milena. What do you think are the current relevant skills that students and young professionals need to develop to become a marine geophysicist or a general geophysicist?
I mean, it's again, it's something that it will depend on what they want to do. But for marine geophysics, what is currently a big topic is really application of machine learning, and I think that that's something that will trend in the next several years. Although there are some. I spoke with people from industry, and they see that there is a starting to that kind of interest is starting to drop, and they are opening much more positions for imaging, for example, for proper seismic imaging rather than using machine learning. So it's really depending on what people want to do and what is the purpose that they want to apply. It's also the fiber optics that is also starting to, or it's actually starting to peak in the way that we try to use better way of recording waves and looking into subsurface. So I think the novelty is going to come. The things that will emerge in 2 years, we probably don't know about them right now. So again, it's really for me. If I would give advice, it's really follow what you are interested in, and um, try to learn as much as possible. One advice that I was getting from Exxon when I was doing internship was that they said we don't really care what you know. We all we care about is how quick and how willing you are to learn. If you have the capacity to do that, we can teach you whatever we want. We have the means to actually teach you. And so, if you develop this passion, and if you develop the way to learn quick and to be open to new opportunities, I think it's no matter what you do, you will do it. You will succeed.
Thank you for sharing that, Dr. Milena. I also think that, yeah, we can apply machine learning, right? But you need to have the domain expertise. So I
Yeah,
think
yeah,
machine learning is to enhance what we're doing, right? But you need to know the nitty gritties of actually what we are doing, right? So
yeah.
yeah, I think that's good. And I agree with Hexon because students like me, we actually get overwhelmed, and we try to hold back and say, oh, I can't apply to this research position because I don't have the knowledge that you think that they're willing to accept for that position. But yeah, it's good that we know that they actually want people that are fast in learning and people that are passionate and that are willing to learn. So thank you very much for sharing that, Dr. Milena. So my next question is, yeah, what are those hard and soft skills that you think junior geoscientists should work on developing?
If we talk about research, I think that there are a lot of skills that people normally don't think about. So some of them are communication. It's really good to have communication skills to communicate with your colleagues, build your network, but also communicate with general public. I think that's a very valuable skill to have. When you write papers now, it's very important to be able to present and illustrate what you have as a result. And so graphic design is one of the skills that is very important. And we don't normally think about geophysics connected with the art and artistic way of representing our results. Writing is again a skill that is important. And as someone who likes languages, I really think that one of the skills that is really good to have is to speak different languages, because you connect with people much better when you speak their mother tongue. And so if you have opportunity and if you have passion for languages, go ahead and learn as much as you can, because I think that's for me it has been really beneficial, knowing different languages and being able to communicate with different people.
Thank you for sharing that, Dr. Milena. So I just wanted to announce to the audience. I think, yeah, mentoring 365 actually, they have some mentorship cycle that you can take advantage of. And I was part of their open science communication, and it was great. So I think communication is actually key because you can't be a great scientist if you can actually communicate what you're doing effectively, right? So I think communication is important. Thank you for sharing that, Dr. Milena. So what advice would you have given your younger self, or would you give your younger self?
So that's something that I thought about, because I listen different podcasts, and then sometimes there people are asked what they would tell their younger self, and most of them respond that they will say to their younger self not to worry, because yeah, everything is going to be fine. I don't think that it would work with me, because at that time you cannot really know what is the result, so you cannot really stop to worry. But what I would tell myself is to be more patient, because things will come. Sometimes they come sooner, sometimes they come later, but patience is something that I still have to practice. It's a skill that I haven't developed, and so I think that patience is something that I have to work on, and not only younger self, it's my current self. So it's yeah, that would be one thing that I would.
Thank you for sharing that, Dr. Milena. So, is there any other thing that you'd like to give us? Your final thoughts? What, yeah, you'd
I
like
would
to give?
like to thank you for this opportunity to participate in SEG event. I'm very grateful actually to SEG, because I received several scholarships from SEG that helped me through my graduate school, to fund some events, to attend some conferences, and to fund different things. And to everybody, I would suggest to be curious, to be led by their passion, and of course to be patient, and yeah, and don't give up. If you like something, be determined, be persistent. The results will come. Do your best. I don't think that you have to be the best. I think that the important thing is to give your best, and then you will be happy with the result. That's more or less, yeah. Give your best.
Thank you very much for that answer, Dr. Milena. Wow, I haven't seen a lot of questions in the chats about your presentation. But if you have any question about Dr. Milena's presentation, please reach out to her on LinkedIn. Her name is, you can see the description of the webinar or presentation. You can see the description, down, and then you can, search for our name on LinkedIn. Can you hear me, Dr. Milena?
Yes, yes, yeah.
Okay. Yeah, I just wanted to ask question on your presentation. You talked about velocity analysis and then that you did that with Shell. So what can you talk to us more about? I just wanted to know how velocity helps with the migration, how you did that. What are the things, the key things? How did you do it? What software
Yes.
did you use?
So I was doing, everything was in house. So all the codes were actually proprietary softwares from Shell. So we used this code that is 3D full waveform inversion, that was developed by one of the scientists who works at Shell. At that time, that was the only code that was existing, in not only in industry and in academia, so in on a global scale, that was the only code that was able to do the elastic 3D full waveform inversion. And that was at that time very important because still there is this kind of like two kind of worlds that are arguing between elastic and acoustic world. So in acoustic world, we assume that everything is behaving as water. So we have only propagation of P waves, whereas in elastic world, we have both P and S waves. In the case that I was actually looking at, the specific rise, shear velocity was very important because we have hard surface, what they call hard surface. It's a very high contrast between water and basalts. So we need to take that into account, and that's why we needed to apply elastic code. And once when the elastic code gave us satisfactory results, we just used this velocity model to plug it in the processing flow to do pre-stack depth migration. It was the standard Kirchhoff migration. At that time, that was the best velocity model that we could produce. Of course, because the streamers that we were using to collect the data are only 6 kilometers long, so that gave us the control only on the topmost 800 meters. So for deeper parts, because the magma body is at about 1.4 kilometers, I had to do residual velocity correction. So it was a lot of back and forth correction of the velocity to actually obtain nice images and reduce as much as possible diffraction tails. But I don't know if that's answering the question that that you
Yes, actually, it does. It does. So I'm also thinking, have you seen any research on, machine learning doing that? Because I think that's something that, I don't know if it's
no.
going to be so complex. So I think that's something that we can look at.
I haven't looked. I don't think that there is, and I think that actually I haven't looked, and I'm not aware of the study that shows full waveform inversion through machine learning that was as intense and successful in solving the problem. Maybe some simpler kind of like synthetic examples they do exist, but something that is real data, real complex geology, I haven't seen. So I think that machine learning is really good when there is some kind of like a typical behavior where you have I don't know a bunch of cases that can actually teach the algorithm how to find a solution. But this kind of particular cases, I think, are still requiring a geophysicist to intervene and actually do all the tests.
Thank you for that, ma'am. Yeah, I actually want to learn more about FWI. So
Hmm.
I'm
Hmm.
really interested in it. Yeah, I think we can. This is a good point to
Yeah.
stop
Hmm.
our session. I just want to say thank you so much for accepting our invitation and joining us here today and to share your experience. Thank you so much, Dr. Milena. And
Yeah.
yeah, have a great day, right?
Thank you. Thank you very much. Yeah. Have a nice day, everybody.
All right, thank you. Bye.
Goodbye.